Hello everyone, today I'm going to talk about chemical reaction path model of epigenetic lead zinc mineralization process with an example from the Century deposit of Northern Australia. Why geochemical modeling? First, to test hypotheses of ore forming processes, such as syngenetic models where base metals are deposited on the seafloor, and epigenetic models where base metals are replacing the host rock mineralogy. But we can also use geochemical modeling to evaluate specific processes such as the role of thermochemical sulfide reduction in triggering sulfide mineralization. This process is described by the following reactions, but the most important part to notice here is that hydrocarbons are oxidized by the reduction of sulfate into sulfides, which also produce bicarbonate as a byproduct. The second reason to use geochemical modeling is to develop some geochemical vectors that may help with exploring those mineral systems. Here is a schematic diagram that describes the carbonate composition from proximity to the ore body to a greater distance, and we can see that iron-rich carbonates are generally closer to the ore body, whereas the carbonates at a greater distance to the ore body are mostly enriched in calcium and magnesium. Now we can use geochemical modeling to predict the variation of the mineralogy and compare these to the observations. The key questions I want to focus on today is, does organic matter matter for sediment-hosted lead zinc mineralization? So this is going back to the thermochemical sulfate reduction. And why we're looking at this is because there seems to be a dual occurrence of organic matter and lead zinc mineralization in many ore deposits, many lead zinc sediment-hosted ore deposits, such as the Century deposit in Mount Isa. Here are a couple of pictures from this deposit, where we see in this photomicrograph that the hydrocarbon in brown are being replaced by porous fluorite. And on the right-hand side is a TEM image from porous fluorite, which shows the minute crystals of fluorite within a sea of bitumen. It's that intimate connection between organic matter and fluorite that make us focus on the Century deposit, but also because this deposit has no metamorphic overprint. And this is important because we can reconcile the results of our models to the observations. The deposit is also well studied. It has temperature and salinity of the fluid, and that's critical for constraining our model. Geographically, the deposit is located in the western fault belt of Mount Isa in Northern Australia, and it occurs on the Termite Range faults. The deposit consists mostly of sphalerite, minor galena, and pyrite, and the ore minerals are hosted in organic rich shales with a TOC of about 3%. The conceptual model that we have used here consists of a meteoric water that circulates at depths, travels through different rock sequences, but most importantly, an evaporite bearing sequence and a basalt. This brine then rise back to the surface through the Termite Range fault and then migrate through the carbonaceous shale. Now, the reason we focus on the evaporite and the basalt, which occur on the stratigraphy of the Century area, is that the evaporite is a source of sulfates and chlorine, and the interaction of this water with this rock will allow a brine to become oxidized and saline. This oxidized and saline brine interacts then with the basalt, and the basalt is a source of base metals, lead and zinc. Now, to understand what's happening here, if we look at the predominance diagram for zinc, we can see that in an oxidized environment, zinc is carried in solution. And therefore the interaction of this oxidized brine with the basalt will allow the leaching of the lead and zinc into solution. This will generate a metalliferous brine, which will then migrate into the carbonaceous shell, and upon entry into the carbonaceous shell, the presence of organic matter of that reductant will cause the sulfate to become sulfates, as per the thermochemical sulfate reduction, and will trigger the deposition of sphalerite and galena. And this is indicated by this arrow here. Now this model is undertaken using HCH, and we've done a 1D infiltration model. So this is the architecture of the model, where we do a step flow-through model. The first step consists of this water plus evaporite, which is then passed through a block of basalt. The fluid is then migrated into the shell, and we look at how the fluid composition and the rock composition vary as we migrate this fluid. In our second wave, we pass the same fluid composition into the basalt and the shell, but the rock composition is taken from the previous wave. So we essentially using our rock composition as a reference frame, and we continuously passing the fluid and altering the rock composition as we go ahead. So just to give you an overview of what that looks like in terms of mineralogy, as we continuously add more fluid into this block of rocks, we start altering these rocks and developing different mineral assemblages. Here's just freezing on a particular wave where we have various mineral assemblages that reflect various pH and redox conditions. We've done those models for two different host rock, one with organic matter and one without organic matter. And what we see is that for the models with organic matter, we have precipitations of carbonates and of sulfides. Carbonates in red, where we see a variation in carbonate composition from manganese-rich, iron-rich, and calcium to magnesium-rich, which is in agreement with what is observed in the field. But we also see precipitation of various sulfides. However, if we take the host rock without organic matter, we do not precipitate carbonate and we do not precipitate sulfide. So this clearly shows that organic matter plays a significant role for precipitation of sulfide and carbonates via the thermochemical sulfate reduction. But of course, organic matter alone is not sufficient. We need a brine that is oxidized at the right temperature and that also has sulfate in solution. So in conclusion, our study demonstrates that using geochemical modeling, we can prove that organic matter hosted in shells has a significant impact for base metal deposition via the thermochemical sulfate reduction. Thank you. And if you have any question, please pop up at the chat.